For 4 billion years, one object has powered almost every living thing on Earth, a star, our sun. And for the last 70 years, a handful of scientists have been chasing an almost insane goal to build a star of our own down here on Earth. If they succeed, it could give us almost unlimited clean energy forever. But the real story is stranger than the headlines tell you. Here's the first thing almost nobody tells you. The core of the sun is surprisingly gentle. Gram for gram, the sun's core produces less heat than your own body, less than a compost heap. Its power density is tiny. The sun is a giant not because its fire is fierce, but because it is unimaginably huge. Trillions of tiny, feeble reactions stacked into something colossal. And those reactions shouldn't even happen. Two protons should never get close enough to fuse. They repel far too strongly. They only manage it through a quantum trick called tunneling, quietly cheating through a wall they can't climb. It's so unlikely that an average proton in the sun waits billions of years to fuse even once. The sun is powerful, patient, and astonishingly slow. So what is fusion, really? You take the lightest atoms in the universe, hydrogen, and force two of them to merge. They fuse into helium and spit out a neutron, and in that instant, a tiny sliver of mass simply vanishes. That vanished mass becomes pure energy, following Einstein's most famous equation, a speck of matter, an ocean of energy. Don't confuse this with today's nuclear plants. They split heavy atoms, fission. Fusion does the opposite. It joins light ones, and it's the cleaner, more powerful side of the coin. On the sun, monstrous gravity does the hard work, crushing atoms together, but Earth has no such gravity to spare. So to make up for it, we have to go far more extreme. Not 15 million degrees like the sun's core, but over 150 million, 10 times hotter than the center of the sun. At that heat, matter tears apart into plasma, a glowing soup of naked nuclei and electrons, the fourth state of matter. And here's a fact that stuns people. Despite those hellish temperatures, a fusion reactor holds less than a single gram of fuel at once, a plasma 1,000,000 times thinner than the air you're breathing. It's less a furnace and more a near-perfect vacuum with a tiny, ferocious heart. So how do you hold something hotter than a star when it would vaporize any material instantly? You never let it touch anything. You trap it in a cage made of pure magnetism, inside a machine called a tokamak. Invisible magnetic walls suspend the plasma in midair so it floats, untouched, in the middle of the chamber. And the reason fusion suddenly feels close isn't a new physics discovery, it's a new magnet. A recent breakthrough in high-temperature superconductors created magnets so powerful they let engineers shrink a reactor from the size of a stadium to the size of a room. There's also a myth worth killing. Fusion cannot melt down. There are only grams of fuel inside. The moment anything goes wrong, the plasma simply cools and dies within seconds. It fizzles out. It can never run away. There's a second way to do it, the opposite of gentle. Aim the most powerful lasers on Earth at a fuel pellet the size of a peppercorn and crush it in a billionth of a second. In 2022, this method made headlines worldwide. For the first time, a fusion reaction released more energy than the lasers delivered to the fuel. History. But here's the part the headlines skipped. Yes, the fuel gave back more than the lasers hit it with. But those lasers drew over 100 times more energy from the power grid to fire. So we didn't actually gain net energy, not even close. It was a scientific milestone, not an energy one. And knowing that difference is what separates hype from reality. You've probably heard fusion runs on seawater. Half of that is true. One ingredient, deuterium, really is sitting in every drop of the ocean, effectively limitless. But the other ingredient, tritium, is one of the rarest substances on Earth. It's radioactive, it decays away in about 12 years, and the entire world's supply is measured in just a few kilograms. So future reactors will have to breed their own fuel, using the neutrons flying out of the plasma to convert lithium into fresh tritium on the spot. No one has ever done this at scale. It may be the hardest unsolved problem in fusion, and you almost never hear about it. So when do we get it? First, a reality check that surprises everyone. The largest fusion project ever built, ITER, will not power a single light bulb. It's a pure experiment. The first plant designed to actually make electricity comes after it, probably in the 2040s. Fusion has been famously 30 years away for 70 years. It became a punchline. But something genuinely changed. Billions in private money and those new magnets have for the first time bent that curve. Serious estimates now point to working pilot plants in the 2030s and real grid power in the 40s. Still not tomorrow, but for the first time it's when, not if. And if we crack it, the payoff is hard to overstate. Clean power, almost without limit for every nation on Earth. No carbon, no meltdown, no running out. Even its waste is different. The reactor itself grows mildly radioactive, but for around a century, not 100,000 years like today's nuclear waste. For 70 years, building a star on Earth was a fantasy. Today it's an engineering problem, and we are closer than we have ever been. If you want to understand the future before it makes the headlines, subscribe. We're just getting started.